Hi, everybody. In this lecture, I will talk about forced vibrations. This is a continuation of the lecture about mechanical vibrations. And just as in there, we'll have a spring and mass system. Now, let's draw a diagram again. So here's a spring. Here's an object attached to it. Now, maybe let us recall the forces acting on it. So we had gravitation, and then the restoring force of the spring. So U is time t. Then we also have some damping force, gamma times V. So V is velocity times t. Now, in addition to all of these, we'll have one extra force. So now suppose you have an external force, F of t, acting on the object. This is an external force. It depends on time. It does not depend explicitly on the position. So it doesn't look at the position of the object to decide, how much force is to be applied, but it only t matters. So it's coming. We model it as something coming from outside, an outside source. Okay. Now, if we would like to write down the equation of motion, first the total force is equal to, okay, mg minus, okay, so I made a mistake here. This is not ku, this is k times L plus u. If you remember the previous lecture about mechanical vibrations. So L was this first initial elongation in the spring, and U was this extra displacement. Okay, so it looks like this, minus gamma times V plus F of t. Now we have mg equals KL. So part of that cancels, and you end up with minus K times U minus gamma times V plus F of t. Now we are ready to write the equation of motion. We use Newton's law. The total force on the object is equal to mass times the acceleration of the object. That brings us here. Now we can use the relations v equals u prime and acceleration equals u double prime. And if we reorganize this, it looks like mu double prime plus gamma u prime plus ku equals f of t. Okay, this is our equation of motion. Now, let's look at this equation a little bit more closely. So, m, gamma, and k are positive constants. Maybe I should also note that gamma equals 0 with no damping case is also possible. Okay. Now, what kind of equation is this? This is again second order. linear constant coefficient. But this time, due to the existence of ft on the right, it is non-homogeneous. Okay, so I guess this is a new ingredient here. We solved the homogeneous case in the previous lecture. Okay, so these external forces cause non-homogeneous terms in the equation. All right. Now, we can solve this equation by using variation of parameters. So solve the equation by using variation of parameters. I mean, this has the advantage of being applicable for any f, right? So you would get an answer for any possible f, but the answer will involve some integrals. Okay, so how would you do this? I mean, I will not choose special values for these things, but just the outline of the solution. So you would need to first find the solutions to the homogeneous equation. M times u prime prime plus gamma times u prime plus k times u equals 0. So we saw how to do this in the previous video lecture. Right, I mean, some fine details depend on the particular values of these constants. You look at the discriminants, check it's if it is greater, equal, or less than 0, and then you have 3 possible cases. Okay, but suppose you did that, and suppose you finished this, and you got UHT equals C1 times U1T plus C2 times U2T. Since the equation is of order 2, you will always get 2 linearly independent solutions. Okay, this was the first step. First you do this, and then apply variation of parameters. So you will need on the way the Wronskian of these two solutions, W, U1, U2. I'll just simply write W in the formulas for brevity. It's equal to, well, you could write like this, U1, U2, U1 prime, U2 prime. It's this 2 by 2 determinant, so it is U1, U2 prime minus U2, U1 prime. Right, this can be computed once you have U1 and U2. And then we derived a formula for variation parameters. So you can get the general solution as follows. It's U1 times integral, okay, minus U2 times f divided by m. I'll explain this divided by m in a minute. Divided by w dt plus U2 integral U1t ft over m divided by w dt. So there's a big formula, but you know, you have a formula. All right. So I mean, computationally, there is nothing that will obstruct you in a sense. I mean, you can find U1, U2, then plug them in here. You know ft, you know m, you can calculate w. So everything in this formula can be calculated. Then there's this business of integration, and that will eventually give you the general solution ut. This will be the general solution. You will have one free constant from the first integral and another free constant from the second integral. So you will have two free constants, C1, C2, coming from the indefinite integrals. And finally, final step, if you also know the initial values, if U0 and U prime 0 are also given, then use them to find C1 and C2, and that will complete the story. Okay, now maybe a moment of thought about why you have this Fm Ft over m here. Where does this over m come from? Now let's go back to the original form of the equation. It's like this: mu double prime plus gamma u prime plus ku. I'm sorry, this is the homogeneous one. Let's look at the original one. Yes, it's here. So mu double prime plus gamma u prime plus ku equals f of t. Now, this is fine. However, everything about this variation of parameters formula was done by assuming that the leading coefficient here is 1. So if you rearrange your equation like this, it's u double prime plus gamma over m u prime plus k over mu equals f of t divided by m. And that's the reason where we have this ft over m appearing in the formula. Okay, if you just write ft, it will not work. I mean, then you would have to change the formula itself. Okay, now this is in a sense, a wonderful answer, although you might say this formula is quite scary at first sight. But the nice thing is you have a formula and it works for all f, right? So the advantage is we have a formula and it works for all possible f. Actually, it is kind of interesting to think about this as an input-output relation. So suppose, I mean, this is an abstract way of thinking about this. So suppose your input is this external force f of t, okay? And your output is your solution u of t. This might be quite sensible. For example, just as a real life possible example of this, this external force could be something coming from outside, like an earthquake, maybe, okay? And the solution ut might be a certain displacement in, let's say, one element in a construction, like, you know, one junction at some point in the building or something like that. Okay, so, and that's quite important, right? So you want to know what happens there, what happens, what kind of displacement happens depending on this external force, so what the earthquake brings you. So then this formula gives you all the possibilities depending on this external force, and that's quite valuable. And one more comment about this. The integrals may be difficult when you try to do them by hand, but in practice, in actual situations, these integrals can be evaluated numerically. And there are quite fast ways to do that. Your computer usually does them for you. So then you would have some very practical way of computing ut in terms of ft. If you say, for example, have the function ft as a graph or a table or some numerical in some numerical format, you can compute your output ut in the same format by doing numerical integration. And this is more or less what is done in practice. Okay. Now, this is nice and general. However, in order to understand some other qualitative features, let's concentrate now on a special case. Special case for f of t. And also, for simplicity, I will assume that there's no damping. So gamma is 0, no damping. And also assume that ft is of a very special form. It is simply cosine of omega times t. This omega is the external frequency. Okay, so it's as if this external force is in the form of a cosine wave, so it's repeating itself with some frequency. You might say it is very special. I mean, what's a cosine wave, right? It's quite artificial. Well, in some sense, yes, but in other senses, no. So this is an example of a periodic function. So cosine omega t is an example of a periodic function. So if you want to understand periodic functions, this is a nice example, but there's more to that. If you want to understand any periodic function, just with any shape, but it repeats itself after a while, right? Then there's a deep result, which we'll also talk about in this course, but towards the end, saying that such functions can be represented as linear combination of cosine and sine functions. So we'll see later that periodic functions, even though their shape might be very different, can be represented as sort of not honest linear combinations, but infinite linear combinations of sine and cosine functions. So, okay, I mean, I was a little bit vague about this, but we'll discuss this later. Now, from one perspective, ft equals cosine omega t is a very special example, but from this perspective, it is like, it's an example, but these are the building blocks. So if you understand these building blocks well, you can then use them later to understand all periodic functions. Okay, but let's concentrate on this particular case now. So our equation is m times u prime prime plus k times u equals cosine of omega times t, right? We want to solve that. Well, first, solve the homogeneous equation. Mu prime prime plus ku equals 0. We did that before, but let me summarize. So you have to write the characteristic equation. Mr squared plus k equals 0. And r squared equals minus k over m. Therefore, r is plus or minus I times square root k over m. We call this quantity omega 0, the natural frequency. Okay, then ut equals c1 times cosine omega 0 t plus c2 times sine omega 0 t. Okay, so these are u1 and u2 if you like. Okay, now you could apply variation of parameters formula, but I will not do that. Instead, let's solve this equation by the method of undetermined coefficients. Now, if you think about it, there are two cases to be careful about. Now, one thing is, I think without loss of generality, we may assume that these frequencies are greater than 0, omega is greater than 0. Otherwise, it just brings, I mean, cosine minus omega t is equal to cosine omega t, so it doesn't matter. And omega 0 by choice is positive, so we are talking about positive numbers for frequencies. Now, there are two cases, omega not equal to omega 0 and omega equal to omega 0. They'll require different guesses for the solution. Right, let's concentrate on case 1. So omega not equal to omega 0. Now let's see what we would guess for the particular solution. Then we'll not have a repetition between the roots on the right and the roots in the homogeneous solution. Therefore, what we should guess is simply a times cosine omega t plus b times sine omega t. So upt equals a times cosine omega t plus b times sine omega t. Now we should plug this in the equation and find a and b. We'll need two derivatives, so let's take the two derivatives. Up prime minus omega a sine omega t plus omega b cosine omega t. And the second derivative is minus omega squared a cosine omega t minus omega squared b sine omega t. Now put these in the equation. Okay, our ODE is mu double prime plus KU equals cosine omega t, right? So if you place them, you'll see that you get m times this double prime plus k times u equals cosine of omega t, right? Now, sine and cosine omega t are linearly independent functions, so I can equate the coefficients of cosines to each other and coefficients of sines to each other. Now, coefficients of cosine, you have minus m omega square a plus ka. This must be equal to 1. And minus m omega square b plus kb must be equal to 0. Now, we can write them slightly differently. So a times, let's do this, a times m times, well, what is left? It's going to be k over m minus omega squared is equal to 1. And b times m times k over m minus omega squared equal to 0. Now, k over m is omega 0 squared, right? So we can write the same equations as a times m times omega 0 squared minus omega squared equals 1. E times m times omega 0 squared minus omega squared equals 0. Omega 0 is not equal to omega by assumption, and they are both positive. So their squares are not equal either, right? Okay, so then this gives us A equals 1 over m omega 0 squared minus omega squared, and B equals 0. Okay, so I guess we got UP now. We scroll up, A was the coefficient of cosine omega t, and B was the coefficient of sine omega t. So we'll get this answer, 1 over m times omega 0 squared minus omega squared times cosine omega t. And if you'd like to write the full solution, it looks like this. It's C1 cosine omega 0 t plus C2 sine omega 0 t plus 1 over m omega 0 squared minus omega squared cosine omega t. Okay. Right, this is our answer. Now, something about this factor, 1 over m omega 0 squared minus omega squared. Now, this factor becomes very large when omega is close to omega 0, not the square. So it becomes large, and it actually goes to infinity when they are very close to each other. So, I mean, there is this business of finding C1 and C2, but still you can show that even when you find C1, C2, it doesn't matter much. And when omega goes to omega 0, the amplitude of ut goes to infinity. This is very interesting because thinking about this as a system, once again, you have some input, which is cosine omega t. Its amplitude is 1. And the output, okay, ignoring the C1, C2 for a moment, its amplitude is 1 over m omega 0 square minus omega square, which can become very large if omega is close to omega 0. So although the input amplitude is constant, the output amplitude is not. It depends on frequency, okay? So output amplitude depends on external frequency. Okay. And it can become very large. Right, so this tells you something qualitative also. I mean, it could be the following thing. I mean, suppose you have a building or some construction, you are shaking it by an earthquake or some by external force. Now, it says that some frequencies are more important than the others, right? So when you build your construction, then it will have certain natural frequencies itself, right? I mean, it will have certain spring-like elements, and they will have their own natural frequencies. And once you build it, you don't change it anymore unless you do some more construction on it. Okay, but then there is this external thing coming, right? You could have different waves, like one wave and another wave much faster. So the slower one has lower frequency and the faster oscillating one has higher frequency. They might have the same amplitude, right? The graphs may have the same height, but their frequencies are different. Although they have the same amplitude, they may have drastically different effects on the output because one frequency might be much closer to the natural frequency than the other. So this is an extremely important parameter in the design of anything, okay? And it's not just buildings. This applies in a similar way to other things like electrical circuits and many other things that you can think about. Okay, now omega equals omega 0 is the limiting case. This is resonance. This is where the external frequency matches the natural frequency. Now, you would think that the amplitude goes to infinity, and that's in a sense right. However, the way we find the solution is not correct because our guess about UP is wrong in that case. So let's look at this once again. Mu double prime plus Ku equals cosine omega 0 t now, and your homogeneous solution is still the same, nothing changed here. Okay. Now, what's your guess for UP should change because you have a repeated root, right? You have omega 0 here, omega 0 here. If you just try a times cosine omega 0 t plus b times sine omega 0 t, you will not get anything. You'll get 0 on the left, non-zero on the right. It will not work. So what you should try instead is to multiply everything by t and write at cosine omega 0 t plus bt sine omega 0 t, right? Let me not do the operations, but plug this in the ODE and find A and B. It can be done. Now, the important thing about this solution is it looks like t times a trigonometric function. So its graph is essentially going to look like that. You'll have some curve like u equals a constant times t. If you want to find the slope of these lines, you have to compute A and B first. But then you have some possibly shifted cosine wave going back and forth between these two values. Now, we cannot really speak about the amplitude of this wave because it certainly goes to infinity. It's not periodic anymore. And amplitude goes to infinity. So this is the picture that you would see when omega is equal to omega 0. You don't have a periodic wave, but rather you have some linearly growing amplitude, and the solution marches off to infinity. You can think about this as the limiting case of the previous case, where omega goes near omega 0. Okay, so this is about all I want to talk about in this lecture. So in this lecture, we studied forced vibrations. We first got a general formula for any external force by using variation of parameters. And then we concentrated on the special case, ft equals cosine omega t, because that's kind of a prototype of what happens for periodic inputs. And we saw this important business of the output amplitude depending on the external frequency, and more specifically, how close it is to the natural frequency. And this limiting case where natural frequency is equal to the external frequency is called resonance. Okay, thank you very much.